Hello, thank you for joining us today. My name is Danielle, and I'm one of your Solid-State Circuit Society staff members. This workshop is being recorded. We welcome you to today's webinar, Education of Microchip Designers at a Large Scale, presented by Behzad Razavi. Please use the chat or Q&A sections to ask any questions in this webinar. I now invite the organizers of this webinar to give a few opening remarks.
Hello and welcome. My name is Xiyuan Tang, and I'm an assistant professor with Peking University and also an IEEE SSCS Young Professional Committee member. I will be the moderator of this webinar, so it's a great honor for us to have Professor Razavi from UCLA here with us. Virtually, he will share us the thoughts about the education of microchip designers at a large scale. So before we kick off this webinar, I will start with a short introduction of who we are and what we do. As young professionals and students, you make up more than 30% of our overall membership, and you are the future of IEEE SSCS. And as the SSCS Young Professionals Committee, we strive to address the different needs and interests of our younger members with initiatives like this webinar today. So here presents some selected benefits of the SSCS membership for young professional members. You will have the access to the SSCS Resource Center, which contains technical tutorials, short courses, and webinars. You have distinguished lectures in your local setting, and there are opportunities to apply for various grants and awards. You will be able to develop leadership skills and make professional connections by becoming a local or global young professional leader. And we also have SSCS Young Professional networking events at all top conferences. And in addition, we have this online mentoring platform. It helps you connect with mentors around the world virtually. So the upcoming mentoring event will be hosted in the VLSI this year, and it will happen on June the 10th, and it will open to all SSCS members and the VLSI attendees. And if you are around, please drop by and check it out. So since 2020, we have hosted webinars for Young Excellence, which is a quarterly webinar series dedicated but not limited to young professional members. And currently there are 7 members to operate this webinar. We focus on technical tutorials and developments. And the webinars are all available at the SSCS YouTube channel. So today we bring you the webinar, the education of microchip designers at a large scale. Although I'm quite sure Professor Razavi needs no introduction, but let me begin with a brief overview for any junior members. Professor Razavi is a professor of electrical engineering at UCLA, where he conducts research on analog and RF integrated circuits. He has served as an IEEE distinguished lecturer and published over 200 papers and 8 books. He has received 9 IEEE Best Paper Awards and 6 Teaching and Educational Awards, and his books has been published in 7 languages. He received the IEEE Patterson Award in solid-state circuits and was recognized as a top author in the 50-year and 75-year histories of IEEE SSCC. He is a member of U.S. National Academy of Engineering and a fellow of the U.S. National Academy of Inventors. And if you have any question, please leave it in the Q&A box, and we will have the Q&A session towards the end. So without further ado, let's welcome Professor Razavi. And I will stop sharing.
All right, thank you for the introduction, and good morning, good afternoon, and good evening. Let me go ahead and share my screen here. All right, let's go here and go to full screen. All right, today I would like to share my thoughts and experience in regards to education of chip designers, especially if we are targeting hundreds or perhaps thousands of students. I will begin with some introductory remarks and talk about the concept of a tape-out class and look at its course structure. Next, I'll go over some scalability considerations, again, as we go towards a very large number of trainees. and show the roles that the instructors and industry mentors can play in such an endeavor. And finally, I will look at the matter of test equipment, which is also a factor in scalability, and talk a little about a center that we have created at UCLA, Center for Education of Microchip Designers, and summarize with a conclusion. The purpose of circuit design courses and education in a university environment is try to emulate product design in industry. And the question is, how do we do that? Well, let's take a quick look at how product design flows. We start out with product definition. We have some specifications that we'd like to meet. Of course, it's an oversimplified set, but it illustrates the concept. And next, after that, we begin to design the chip and do the layout for the chip. In today's technology, the circuit design and layout design are so intertwined that this iteration starts almost from day one and continues throughout this process for about 1.5 years until we have completed the design and the layout, and then we send for fabrication. Fabrication takes 3 to 4 months, and after that, we receive the circuits, we package them and assemble them, and then we begin test and characterization. So this entire effort is a matter of 2 years, a little more in industry for a typical product. But we would like to abbreviate that so that it fits in our academic schedule. Now, there are a number of considerations here, possibilities. If you look at typical course structures that we have in universities, we could just have a standard circuits courses where we teach them the concepts of circuit design, and we go over some basic building blocks. So that's about half of the material that you would see in a chip design course. Or we can have a standard circuits course that also has some design projects. So that tries to complete this step of chip design at the circuit level and at the schematic level. But of course, if we stop here at the end of this course, we are missing all these other steps that we would need to complete before students have enough experience and confidence in their capabilities. All right, so then maybe what we should do is also add layout to the sequence. Maybe in the same course, some courses do allow layout at the end or encourage layout at the end. And again, that's to show the effect of parasitics of the layout and the procedure for layout and extraction and verification. And that's great. However, as long as the chip is not fabricated, we are still missing these last steps of this entire flow. Okay, so then maybe we can also fabricate the chips. And in fact, in some universities, they do fabricate the chips, but they may not get to the point where they can test the chips. And for that, I would like to bring to your attention this statement. If you haven't tested it, it doesn't work. This is attributed to different people, by Caldwell, Roskill, etc. But whoever said it, it's a profound statement indicating that it is only after we test the chip that we actually understand the entire flow, understand how good our design is, etc. So we do need to, after fabrication, reach packaging and test and characterization. See if I can minimize this window somehow. So the purpose of such a course in a university environment is to go through all of the steps from left to right to emulate what's happened what happens in industry. All right, so this brings us to the concept of the tape-out class, and this was originated perhaps in the 1980s by John Newkirk, Rob Matthews, and Mark Horowitz at Stanford, and has been practiced for decades in different universities, and it's become more popular in the past 10 years or so, and that's what we would like to pursue here. In these courses, we have mostly graduate students and some undergrads, and there are different structures for these courses. What I will present to you is what we have at UCLA, which is based on a quarter system. So the idea is that in the fall quarter, we have conventional chip design courses, analog and digital, at the graduate level or advanced undergraduate level, and students take those. Then in the winter quarter, they take a 2-unit course in which they design, lay out, and verify certain building blocks. And at the same time, they also try to define their main project topic, the topic that will lead to the final chip design. Then in the spring quarter, for 4 units, they delve into the design, layout, and verification of the final chip so that they can submit it for fabrication at the end of May, early June. The fabrication occurs over the summer. They also are engaged in PCB design and test plan, and then the chips arrive towards the end of the summer, and then they test and characterize the chips in the fall quarter. So this sequence allows them to design chips, fabricate them, and test them. And it has a number of attributes that are worth mentioning. The first is that the instructor has a 1-year sustained and substantive interaction with the students. So the students get to benefit from the instructor's experience and knowledge over this time period. Another is that we count only this course in the spring quarter toward their degree requirements, but they have to take all of these courses, all 3 of them. And finally, to ensure that the students stick around and actually do the testing in this fall quarter, I release their grades only after testing is completed here. And so they get an incomplete, and it is only then that they receive their grade. As I said, as long as they don't test their circuits, they actually don't know whether they did a good job or not. All right, let's talk about the first course. In our sequence is 2 units, and it deals with the design and layout of building blocks. This is only 2 hours of lecture per week, and I talk about all of these in these 2 hours for 10 weeks. CMOS design flow, layout concepts and examples, multi-finger transistors, the interconnects and their parasitics, design rules, passive devices and ESD, latch and flip-flop design, comparator design, symmetry and mismatch, analog and digital I/O, packaging, LC/VCO design, and capacitor DACs. And in parallel with this, they will also do homeworks. Homework assignments deal with design, simulation, layout, and verification of a ring oscillator, a divide by 2 circuit, a strong arm latch, a receiverable static register, and an LC oscillator. We are using TSMC 180 nanometer technology for this work. Now, these building blocks are chosen very carefully. Number one, they grow in complexity as we start from the ring oscillator and work our way up. And number two, they actually become certain useful building blocks for their final chip design. And many of them end up having some of these building blocks in their final design. And the key point here is that as in these 10 weeks for the first course, they get to see how layout and its parasitics affect the performance. And they calibrate themselves with respect to that so that when they are designing circuits, they have a feel as to how much degradation they should expect in the performance as after the circuit goes to layout. All right. Then one of the issues is that if you have a large class, for example, I have 70 students in my class this year, how do I check the students' work? Every one of them is doing design and layout of building blocks in this first course. And things become more complex as we go to, for example, the second course, where we have a large number of chips. Right now, we have 35 chips that have to be reviewed by me so that they don't make any mistakes. So in the first course, they bring their work on a flash drive to class. And what I do is I just randomly select a person to come to the front, plug in the flash drive, and present the work. And then we critique that work. Sorry about these misfires of the keypad here. And this allows them to receive some feedback from me and also from their peers in the class. Everyone sees everyone's work and the flaws that might reside there. All right, then at the same time, students begin to define their projects, and we'll talk about the topics shortly. But I impress upon them that the topic has to be chosen to satisfy these 4 conditions. Number one, the circuit must be able to be taped out by the end of May. So that would be right here, around here. So they define the project sometime here in, let's say, December or November, and then they have to finish it sometime in March, and they have to finish it by end of May. Number two, the circuit must be able to be tested with the equipment that we have available to us in our lab. And number three, the circuit must be able to be designed and completed by two partners. And number four, they should be able to completely extract and simulate the circuit at the transistor level in cadence. Now, the last two conditions may or may not apply to all courses. In some courses, instructors prefer to have a larger team size and a larger, more complex chip, and that's fine. To me, the number two for partners is sort of optimum in that the chance of miscommunication and making mistakes are lower. Also, in terms of fully extracting and simulating the circuit in cadence, again, if it's a large digital chip, maybe they don't need to do that as long as they rely on accurate and correct simulation tools, starting from Verilog and placement and route, etc. All right. So the topics that we have in these courses are quite varied. We have A to Ds, PLLs, oscillators, DC-DC converters, RF circuits, receivers, transmitters, decision feedback equalizers, CDRs. And in fact, this year we even have a cryogenic amplifier, we have blood pressure sensor, we have neural sensing amplifier, compute memory processor, etc. So I do give them enough latitude to select their own projects, provided that they meet those conditions. Okay, let's talk about the second course where the bulk of the work occurs right here in the spring quarter. And in these weeks, it's about 9 weeks, 10 weeks, I do need to be with them almost every moment of every day to make sure that they are on the right track, they do go on off tangents, and they are constantly reminded that layout and verification do take a long time. So when they start designing the schematics here, they should allow themselves enough time to finish the layout and verification by the end of the spring quarter. To make sure that they're not making mistakes, I conduct what I call rapid fire 5-minute design reviews with every team once a week by Zoom. And I'll talk about that more a little later. And but then I defer more detailed questions to my office hours. In week 7, I actually go into the students' cadence schematics and start from the top level and look at every single block and every single transistor and give them feedback and action items to follow. And in week 8, I do the same thing with their layout to make sure that the layout is also at least sound, not necessarily perfect, but at least it will be functional. All right, so let's talk about the scalability a little bit. We are targeting a large number of students, 70 to 100, and later on, maybe even hundreds or thousands. So exactly how do we go about doing that? Well, we have produced a number of training videos, especially when they start out in terms of the mechanics of design, layout, and verification of building blocks. And that helps students get started right at the beginning of this quarter, the winter quarter for the 2-unit course, so that I don't have to sit with every one of them, or I don't have to teach some of these in class. And these are not very long videos. Each of them is about half hour to 45 minutes. But it does help the students tremendously because they follow it step by step. For example, to design, layout, and verify a ring oscillator. I also, as I mentioned, I have these 5-minute rapid fire reviews with the students on Zoom. And this means that every team is reviewed every week for all of these 9 weeks to make sure that they are on the right track. Another component that I found extremely useful is to assign mentors from industry to each team so that they also shoulder some of the load in terms of supervising or overseeing the work of the teams. So more on these a little later. And finally, another impediment to scalability is the test equipment. We will see that actually we need a large amount of test equipment, lots of instruments, and we'll see how we can manage those. All right. So when we have these tape-out classes, one of the questions is how detailed should the reviews be, meaning how involved should the instructor be in the course material or in the projects? Well, in my opinion, they should be very detailed. And this is particularly in response to what students often say. They say, but it works in simulations, so what's the problem? It should work in practice. So our job is to show them all the factors that make a circuit fail in practice, even though they may work in simulations. For example, suppose you have a phase lock loop, and they put these two things together and may even work in simulations. They have an LC oscillator, pretty complex with all the components, but then a bunch of questions that we need to ask. For example, where did the inductor model come from? Is it a garbage in, garbage out situation, or is the model accurate and reliable? So in fact, to that end, I have asked my PhD students to create a library of inductors and simulate them in EMX and produce both the layout and the model so that the students in the class, in the tape-out class, can use without any modifications. Or for example, they are simulating the circuit, but they're not looking at the voltage across the current source. The current is initially ideal and everything is good, but when they put the transistor in there, it turns out that that node, the tail node collapses and the transistor is no longer in saturation. So the circuit is not working very well. Or they have this switch as 0 and they don't know how to size it so that it does not degrade the Q of the tank. So many of these details that we assume that they may know, but they may not, because we're not teaching the details of all of these in this class. They're supposed to know this stuff from other classes, but maybe they don't. Similarly, when they design this frequency divider, let's say there's a divide by 2 at the input of this MMD, and this divide by 2 based on C-squared MOS has charge sharing problems. So when they look at these waveforms and they see the charge sharing right here between the capacitance at node N and the capacitance at node C, and they see a kink in the waveform, do they understand how this kink will affect the performance? So lots of details that we do need to keep track of when we are interacting with the students. Here's another example, they're designing a SAR A2D, and that's great. Oftentimes they just look these up online, and I'll have more to say about that, but are they aware that, for example, this logic has to be designed properly? Most of the students who come to my class have already taken a digital VLSI course. But for some reason, when I tell them to design a restartable register, they freeze. For some reason, they don't have that knowledge and they have to start pretty much from scratch. Or when it comes to the DAC, are they aware the DAC faces mismatch problems? And when they build the DAC either as a binary array or a thermometric array, do they know that the layout of this DAC has to be exact and precise so that every cell sees the same environment around it? Believe it or not, I have repeated this in my class this quarter probably 20 times, and they still have difficulty understanding what we mean by every cell seeing the same environment. All right, so I mentioned that the reviews are in a rapid fire session. This is what I call type 1. So we have 35 design reviews per week. Each group has 5 minutes and present on Zoom. It's a lot faster than in a classroom environment because they can quickly switch in and out of Zoom. I need to identify any issues that they have and any risks that they are taking with respect to their circuits. And the good thing is that, for example, all the students who are working on phase lock loops are in the same session, so they all learn from each other's issues. Here are some examples. Team 1 working on a 6 GHz PLL. I have to tell them that make sure the maximum VCO frequency does not exceed the maximum divider frequency. Because if that does, then while the PLL is trying to lock, the divider fails, and the PLL never locks. Or another team, they say how much ripple is acceptable on the control voltage. Well, I have to explain to them that they have to measure the output spur level or the jitter to see if it's acceptable, like it meets the specs. Or team 3 says are looking to decide how much the VCO swing is necessary, and I have to explain to them that the swing is should be large enough to drive the frequency divider in the slow corner if it's directly connected to it. So all of those have to be conveyed. In another type of rapid fire session, as I mentioned, I actually go through their circuit schematics in Cadence. So they give me control over Zoom, and I start from the top level and descend into every cell and look at every device and ask about every voltage and current and give them quick action items to follow. I repeat this entire process for the layout as well. The layout is very critical because they simply don't have enough experience in terms of various issues that might jeopardize the performance of the circuit. All right, I mentioned industry mentors as a great component to add to this class. So they help with the instructor in that some of the work or some of the oversight can be delegated to them. The commitment they have is not a whole lot, 1 hour meetings with the team once a week for 9 weeks. And the mentors like this task because they get to work with fresh blood, and it also opens up opportunities for future recruitment of the students. As you can imagine, such an effort is fraught with many pitfalls. Here are a few that may prove detrimental, and that's why I have brought them here. Number one, the instructor may underestimate how long students need for design and layout. So the students come along and say, we want to add this feature or that feature, and the instructor agrees, not realizing that this will cut into the time they have for finishing the entire project. Similarly, the students themselves may underestimate how long they need for design and layout. And again, it's the instructor's job to keep telling them to cut this out, to cut that out, and keep the circuit simple so that it can actually be finished. Many a time, students find ideas online and implement them without understanding how they work. And this is also bad. I say, if you don't understand how a circuit works, it will probably not work at all. So I have to impress upon them to make sure that they actually understand. And a lot of times, of course, the ideas you find online are even incorrect. So they have to be aware of that. Many a time, students do not take into account package parasitics as they approach the final integration of the building blocks and connecting to pads. So those have to be included. And finally, sometimes the instructor may not appreciate what the test and characterization phase may entail, especially in terms of the equipment that's necessary for it. So it could be that students design the circuits and that they get them back from fabrication, but now they have to test them, and the instructor and the students realize that the test equipment is expensive, not available, or even doesn't exist. All right, let's talk about what happens after tape-out over the summer. The students will deal with PCB design and test plan, and I have a few words to say about that. The test plan includes everything that they need to connect to their chip, how the chip lands on a PCB, and what input stimuli they have to apply, in what form, bias-tees, balance, SMA connectors, how they will sense the output to the pin headers or SMA connectors, and all the voltage sources, logic analyzer over here, signal generator over here, and various specifications for these things. They need a clock generator at 50 megahertz and so on. So all of those have to be accurately documented so that when the chip arrives, they know exactly what they need. This also helps the instructor decide how many pieces of equipment and what type of pieces of equipment are necessary for testing and characterization. All right. The test plan also includes a bonding diagram that they have to create. Initially, we were bonding directly to PCBs. So here are some diagrams. On the left, we have the overall diagram. It shows that this particular chip on the bottom left connects to these traces on the PC board. And the one on the right has a slightly different plan where we cut the chip and we place it in a smaller cavity, a smaller ground paddle, and again, it connects to the pads. Nowadays, we have switched to packages, so the packages are standard, and that allows us to simplify the bonding phase of the work. For PCB design, we have also produced videos, so they follow those step by step, and there are vastly different considerations. For example, on the left, we have a PCB for an RF receiver, whereas on the right, we have a PCB for SR A to D. So the design considerations are very different, and that requires that the instructor also have a review session and look over all of the PCBs in terms of everything that can go wrong, all the couplings that can occur, all the parasitics that can affect the performance, and give action items to the students to correct these PCBs. This all happens over the summer. All right, and finally, we arrive at the fall quarter where the chips have been bonded and packaged and everything, and we are ready to test them. The students populate their PCBs and test their circuits. And again, the instructor needs to be there all the time because, again, students don't have much experience with test and characterization. All right, so when we get to the test phase, we also face a scalability issue. It is true that, for example, with 35 chips, not all of them have to be tested at the same time, but still some 10 or 20 of them do have to be tested at the same time. And the question is, how much equipment is necessary for testing all of these circuits? We have, of course, analog chips and digital chips, and we have various pieces of equipment that are necessary. For digital chips, we have logic analyzers, FPGAs, pattern generators. For analog chips, we have all of those, and then RF generators, bit rate testers, scopes, spectrum analyzers, and noise figure meters, and so on. So just to give you an idea, if you want to test an RF receiver for IP3, we need 3 RF generators. To test an A to D, we need 2 RF generators. So once we have 10 or 20 of these in the lab, we end up with tens of RF generators that are necessary for testing these circuits. But beyond the typical equipment that we have in a lab, power supplies and low frequency oscilloscopes, etc. So how do we go about accumulating this amount of test equipment? Well, there are 2 practical options. One is used equipment, and we do resort to that in some cases if the equipment is expensive. And another are USB-based devices, which are actually quite useful and very simple and very inexpensive. As you can see on the bottom, this is a simple device with a USB connection and an SMA connector on the other side. It's an RF generator that goes up to about 6 gigahertz. And it's quite cheap. So we buy this, we connect it to our laptop. It has a driver, creates a display on the laptop, and then we can program the frequency and the amplitude that we want for this generator. And it produces the output through this SMA, which connects to a cable and goes to the chip that needs to be tested. So these USB-based devices come in all sorts of shapes and flavors and so on. So here is a table of what I have used. So the one that I just mentioned is on the top. That one goes up to 6 gigahertz, costs $350, and we bought, for example, 20 of those. And there are other ones that go up to other frequencies with different types of performance. They're more expensive. Then there are logic analyzers and pattern generators, again, USB-based, and at a moderate cost, all of them. So these are good pieces of equipment to have in the lab. We have spectrum analyzers, again, quite cheap compared to what we can buy from Agilent or Keysight for tens of thousands of dollars. And then we do have some equipment that's more expensive, for example, for bit rate testing, $5,000, and for high-speed oscilloscopes, again, $5,600. So that's an example of a collection of instruments that will allow us to test a large number of chips at the same time. All right. In the remainder of time, I would like to raise the following question. How do we go about from, let's say, 70 to 80 students that we have today to larger group, 500 to 1,000 students. How do we train them this many per year? So to address this, we have now Center for Educational Microchip Designers at UCLA, CMID, and I'll talk about what the center does and what its mission is like. So our mission is to create end-to-end training for hundreds of students and engineers. And by end-to-end training, I simply mean what I showed you before. So we want to start from product definition and go all the way to test and characterization. So we want to create tape-out courses, not just at UCLA, but at other universities as well. We have 12 industry partners that are eager to work with us and help us in different aspects of running this center. And here are our objectives. We want to launch tape-out classes across a broad set of universities so that they can all benefit from this infrastructure that we have created at UCLA. We want to methodically educate professors so that they can run their own tape-out courses. And at the same time, we want to create an exciting experience for both students and instructors so that they see the beauty of circuit design and testing and are not frustrated by CAD issues or foundry bugs and so on. We also provide mentors from industry to every design team, just the way I have done it for my students at UCLA. And interestingly, this entire effort can also be applied to practicing engineers. Engineers don't have to be enrolled in a university to benefit from this program. This program can also help engineers who want to gain experience and become chip designers. All right, we do face a few challenges when we have such a large scale of tape-out courses across universities. One is, of course, professors have limited bandwidth. So we want to create a scalable model. As I mentioned before, we have only one process node, TSMC 180, so that PDK maintenance is minimal. We want to shorten the students' learning curve so that they don't lean on the instructor too much. And for that, we are creating a very wide compilation of training courses on everything from design and simulation of building blocks to layout and extraction, I/O and ESD, packaging and PCB design, test and characterization, so that the instructor just says, go watch those videos as opposed to try to teach the students directly. And of course, we also provide industry mentors who accept some of the responsibility for supervising the design teams. The second challenge that we have is that professors have a limited expertise when it comes to tape-out courses. Maybe they haven't had this experience at all, or maybe they are focused on a few fields, whereas students want to try many different fields. So we are also creating training courses for professors and also establishing the trainer workshops so that professors can learn how to run tape-out courses. And then we also are producing videos that allow professors to cast a wider net and venture into other fields. For example, how to design a low-noise amplifier, how to design an oscillator, how to design and lay out and verify a D2A converter, etc. All right, the third challenge is tape-out itself. Especially for professors who haven't done this much, it does look like an overwhelming task. So we want to simplify the work that every university has to do to get to that point. So again, as I said, we have only a single node and a single version of that node. We go with a mature technology and SPDK, so there are no bugs, nothing to worry about. We avoid open source tools because they have lots of bugs. They are not integrated well. So we just use Cadence and Synopsys tools. We go with a reliable foundry interface, Muse, and we also provide standard path frames, standard packaging, and so on, so that all the universities follow the same backend, so that there are no confusions and no mistakes. We also absorb the task of final integration of the project so that the other universities don't have to worry about that. And the last challenge is test and characterization. As I mentioned, we need lots of equipment, especially if we have all these universities, let's say 500 students trying to test their circuits at the same time. So we are creating an instrumentation distribution center at UCLA where we accumulate enough equipment and then we lend this equipment to these participating universities so that they can test their circuits and then return the equipment for the following year. These are the piece of equipment I mentioned to you. So the top one is a USB-based spectrum analyzer. So you see that it has two SMA connectors on the left. Actually, it's not USB-based, it has its own display. And this is a logic analyzer, and on the bottom, we have an RF generator. All right, so here's the overall structure of our program at CMIT. The instructor submits an application, we review the application and determine what level the tape-out course would be. Then we train the instructor for that tape-out course. The instructor begins to offer the tape-out course at each university. At the same time, we provide TA funding, and we also help the instructor find mentors for the design teams. Then the students begin to design their circuits and eventually submit their chips. At the same time, the instructor working with the students will tell us their packaging and PCB design needs so that we can supply the right training material to them. The instructor also decides what test equipment is necessary for all the chips that eventually come back from fabrication. Then over the next few months, the chips are fabricated. We also support packaging and PCB design for these groups, and we lend equipment to universities. And then eventually, with all of these, the students are able to test their chips and see the exciting results that follow. All right, the process node that we are using is TSMC 180. It has 6 metal layers, and the fabrication cycle time is about 1.5 months, so it's pretty quick. And these are training videos that we are creating for this process node so that every student in every university can benefit from these videos at the starting point. So how do we design and simulate and lay out a ring oscillator? We have an inductor library with EMX models, a capacitor library with models. Then we have videos on design and simulation of latches and flip-flops and registers, also layout and extraction, and again, design and simulation of LC oscillators and layout and extraction, placement and route, and scan chains for digital design. So the hope is that once this infrastructure is available, the students can readily jump in there. It's a coherent and cohesive set of videos. So they don't have to go online and resort to any random resources available online. They can rely on what we are offering them. All right, in conclusion, I hope that I have convinced you that it is possible to provide end-to-end training to a very large number of students and practicing engineers so that they become confident chip designers. To this end, instructors do need to be heavily involved in the process in every step of it. And the result is that students and instructors will love the results. Thank you for your attention.
Thank you, Professor Razavi, for showing case the IC design education. It's very inspiring and educational for young professionals. So now let's go to the moderated Q&A section. And if you have any question, please use the Q&A panel. Yeah, and it seems there are a lot of questions. So maybe let's get started. The first question is like, is the PDK you use open source? And if not, how do you handle the NDA related issue?
A good question. Yes, the PDK is not open source. TSMC does not allow it to become open source. So that NDA has to be established between the university and TSMC. But Muse acts as an intermediary these days. So typically, I just asked each university to contact Muse, and then they work it out with Muse. And apparently, it's not a very difficult process.
Gotcha. Gotcha. And also another question related to the PDK. So any reason to choose 180 nanometer technology, but why not a more advanced one?
Good question. Well, there are certain trade-offs. Number one is the cost. When we have 500 students and we use the rule of thumb of 0.4 square millimeters of silicon per student, so that's 200 square millimeters. That amounts to, for TSMC 180, it amounts to $200,000 for one tape out. So as we go down to more advanced nodes, then the cost will go up, and eventually it's not really feasible. The other issue is the fabrication cycle time. So here it's only 1.5 months, so it fits our schedule very nicely. Even though some schools may not want to extend it to the summer, they may just want to do it over the spring. That still fits them. But if we go to more advanced nodes, we're talking 2.5 to 3, maybe even 4 months. And again, that cannot be accommodated easily.
I see. I see. And there's one question about the reliability. Does the course consider the EMIR simulations and other reliability simulations before taping it out?
No. So the only consideration is what I convey to students is that when they receive their chips back, they do not know which corner of the process the chips are from. So, for example, they could be in a slow corner. So they do have to simulate in the slow corner, maybe fast corner, to make sure that the chip does not fail. But beyond that, we don't do anything else because the time is very limited.
I see. I see. Yeah. And what do you consider to be the optimal team size for a group of students to take a chip all the way, like to tape out without compromising the quality or the learning experience? The optimal team size.
Yes. Well, right. So as I mentioned, in my opinion, 2 is probably optimum. But again, it all depends on the type of the project itself. So for example, a PLL or an A2D or an RF receiver or transmitter naturally lends itself to partitioning between 2 partners. So it's pretty easy, pretty quick. But if you have a more complex system, then it may take more people. Interestingly, I have a group designing an FFT engine this quarter without cell libraries, and still 2 partners managed to do that. They designed every building block themselves. They laid out every building block themselves without any cell libraries, without placement and route, and they designed this entire FFT engine. Now, of course, it's not a very large FFT engine. It's reduced, but it performs the same function. But for more complex systems, I know some other universities have a team of maybe even 8 or 10 people per project. And so long as the instructor feels confident doing something like that, and the instructor knows that the chance of miscommunication and mistakes will be low enough, then that's certainly a possibility.
I see. I see. Yeah, that totally makes sense. Yeah, there's one very specific question, like, do you set any prerequisite knowledge for the students who can join this course?
Yes. So for our internal course, what we have is, where was the course structure? They have to have taken certain courses over here before they enter the tape-out course. So these could be advanced undergraduate courses or graduate courses. Now, for our center, the idea is that we will have certain assessment tests that we will offer to instructors of different universities. They will give the assessment tests to students to see if those students are prepared to take their tape-out courses.
I see. I see. Yeah, that requires a lot of support. Yeah, and when you describe there's a few students who works on the same project, how do you divide the work So will it be more like one people designing a part of the project, or one people doing layout, one people doing schematic? Like what's the kind of common divide of the work?
Right. So what I would like to see is that every student gains experience for the entire design flow. So the work has to be partitioned such that every student does circuit design, layout verification, and everything. So a PLL is simple enough to divide an A to D, receivers, etc. Some of them are more complex, but generally students actually themselves decide how to divide these up. I do just have to take a look to make sure that the work is fairly divided between the partners. But typically they both engage in every aspect of the design. So they naturally divide up the building blocks. One person designed this many building blocks, another one this many, and then they try to integrate everything.
I see, I see. And based on your experience, what's the success ratio of the working chips in this course? Like, let's say first in terms of the percentage of the functional chips, and also the percentage of the chips that achieves the desired performance.
Right. So the last time I taught this course, we had 25 chips. We had 50 students. And of these 25, 20 of the chips worked, were functional, and were doing well. And of those 20, I would say maybe 16 or 17 of them met the specifications.
That's pretty good. That's pretty good.
Right.
Yeah. Yeah. So then how do you grade the chips which does not work?
Yeah, so that's an interesting question. And I typically do not penalize them if the chip does not work. I don't say that at the beginning, it's only at the end. But interestingly, students themselves are extremely eager for the chips to work because that's the result of 1 year of activities and hard work, right?
That's right.
So it's not that the students themselves do not spend all their effort trying to make sure the result is correct. But yeah, so I don't, as long as the students have done the work, and during my close interaction with them, I have seen how they work, how they operate, and what issues they may face, then I do give them a grade.
I see. I see. Yeah, and do you have any suggestions to decrease the expected time for the chip design, like from the design all the way to the measurement? Any suggestions?
Well, right. So if we go, so what I showed you was for a quarter sequence. For a semester sequence, some of these can be shrunk. So in fact, I know some schools try to actually have the chips fabricated in spring so that they can test them right around here, even before they get to summer. So there are examples of that out there. So I'm sure that's possible. But it does require some rearrangement or repartitioning of these tasks. So we might have to actually move some of this design and layout of building blocks to the conventional courses. This cannot be done too much because then these courses suffer themselves. So some of these building blocks can move over there, and then some of them can move to the next semester so that the next semester has some layout and design of building blocks and then the final chip itself. So yeah, there's not much we can do in terms of shrinking the schedule because it's the nature of the beast. It is going to take this much time, and the students do need that much time. If we try to shrink the schedule too much, there's a very high chance that chips won't work, and that's not good for anyone involved.
Yeah, that's right. So like in terms of the project selection, like what criteria did you use to select the project topics for the chip design, and how do they align with the industry needs?
Yes, so the project topics are all based on what I feel would be useful to them when they go to industry. So based on my own experience and so on, these are some of the ones that I suggest. Now, when they come forward with their own idea, I just look at the feasibility of the idea and the complexity. The complexity has to be moderate in that it should be handled by two partners in our example. and at the same time should be educational enough. So for example, we have a cryogenic amplifier that has a bunch of features, so they can test it at minus 200, I don't know, 69 Celsius. And we have a blood pressure sensor that has some processing of analog signals and so on. So it's all based on, besides those four criteria that I mentioned, is also should be educational enough and not too simple, because if it's too simple, they don't learn much.
That's right. Yeah, I totally agree. And when talking about the industry, like how to find the appropriate and sufficient mentors from the industry. Like, of course, we are also running mentoring events, right? And how do you motivate the mentors to accept the task?
Yes. Well, so I have graduated nearly 40 PhD students. So they're all working out there, and those were the first candidates I have. I have to sometimes twist their arm a little bit, but they agree generally. And then what I do is as soon as the students in the class have defined their topics, I try to match experts from industry to those topics. So that's essential because we don't want someone who is not knowledgeable about a particular area to try to mentor a group. And then I try to match them, and it takes a bit of work, but it's not impossible. So right now we have 35 mentors for 35 chips.
I see. I see. Yeah, that makes sense. Yeah, and another very important question is how do you address the funding or expenses associated when operating this program that actually cost a lot, right?
Yes, so the program I mentioned, CMID, is funded by the U.S. Department of Commerce.
Uh,
And presently, so if you go back here, we have funding from the government to support this program for 2 years. And then after that, we are hoping that companies will pitch in and they can sustain this effort.
I see. I see. That makes sense. Yeah, there's one specific question asking if the videos you mentioned for the PCB and the layout will be shared or like is it available online?
They are not directly available. I think at some point we will create an infrastructure in our center. We have a bunch of resources available. We will have them available. And then some of them will be publicly available. Anyone can use them. Some of them will not be because, for example, if we are talking about TSMC's technology and circuits and so on, those are protected by TSMC NDA. So those will be password protected. But for the general videos, they will be available to the general public.
I see. I see. Yeah. Due to the time limitation, maybe let's have the last two questions. Like looking ahead, how do you envision the program to keep pace with the rapid advancements of the semiconductor technology?
Yeah, so the fact that we are using an old technology does pose a question as to are the students prepared to get involved in these advanced nodes? And yes, there is some concern about that. We are thinking of perhaps accommodating another node sometime in the future, maybe a 16 nanometer technology or something along those lines. But as I mentioned, there are two concerns. One is the fabrication cycle time,
Right.
and one is cost. So we have to work out the logistics.
Mm.
And if those issues are resolved, yes, we will have another node available as well.
Okay. Yeah. And the last question is like how many working hours do the students put into the course or project, like from the definition all the way to the tip out? Like usually how many hours
Yeah, that's a good question.
per week? Yeah.
So if I were to estimate, going back to our course structure, we have probably in the first course, it would be maybe 40 hours total. In the second course, it is probably maybe 100 hours. In the summer, maybe 10 hours. And then in the fall quarter, maybe another 50 hours. So we're talking probably a total of 300 hours.
I see. That's quite intense.
Yeah.
Okay, yeah, due to the time limitation, let's conclude the audience Q&A session, and thank you audience for all your excellent questions. And on behalf of the organizing committee, I would like to once again thank Professor Razavi for sharing your insights on the IC education. And thank you. And thank you all, and have a great day.
Thank you very much. Have a good day.
Thank you, everybody.
Bye.
Have a great day.
All right,
Bye.
bye.
Yeah, bye-bye.